Здравствуйте. Большое спасибо, что пришли. Мы начинаем церемонию награждения совместного конкурса Siberian Capital и факультета математики Высшей школы экономики работ по теории вероятностей. В конкурсе приняли участие студенты московских и санкт-петербургских вузов. Мы получили на конкурс 17 работ, насколько я помню. Члены жюри меня поправят, если я ошибаюсь. Поэтому мы можем уверенно сказать, что конкурс состоялся. Сегодня у нас достаточно насыщенная программа. С нами все члены жюри. Они поделятся своими впечатлениями, собственно, подведут итоги, назовут победителей, расскажут, как им понравились работы, какими критериями они руководствовались. А потом, собственно, нас ждет выступление представителя нашего спонсора, после чего мы перейдем к, собственно, математическому контенту, и нас ждет очень интересный, вероятностный, конечно, математический доклад. Я передаю слово Константину Михайловичу Ханину, председателю жюри. Костя, расскажите, спасибо. Чем все закончилось?
Спасибо, Саша. Но я, во-первых, хочу сказать от лица всего жюри, что мы надеемся, что это не закончилось, а что это будет продолжено, и что это первый из мероприятий вот таких важных. Потому что присуждение премий это важно во многих смыслах, потому что не в том, даже в том, чтобы выделить кого-то и не выделить других, а в том, что это привлекает внимание к научной работе, к тому, чтобы студенты занимались научной работой. В русских традициях часто студенты занимаются наукой уже начиная там с 3-го, а иногда и раньше курсов. И это замечательно, потому что это лучший способ вообще как бы изучать математику. Значит, было подано 17 работ. И мы считаем, что для первого конкурса это хорошее представительство. Работы были в разных областях. Некоторые были более вероятностные, некоторые были менее вероятностные. Во всех был какой-то вероятностный такой оттенок или элемент, но некоторые были более вероятностные работы. И жюри, конечно, пыталось отобрать, поскольку это конкурс работ по теории вероятности, смотреть больше на работы, в которых вероятность была представлена в большей степени. Значит, второе обстоятельство состоит в том, что был спектр участников довольно широкий. От третьекурсников до аспирантов, до людей, которые уже довольно далеко продвинулись. И, видимо, давно, ну, не первый год занимаются научными исследованиями. И в таких случаях сравнивать работы довольно трудно, потому что это как бы как разные весовые категории, может быть, немножко. Вот. И мы с интересом смотрели на все работы, и мы хотим отметить, что нам очень нравится, как научные руководители работают со своими аспирантами и студентами. И было несколько представителей разных руководителей. Вот Гастников Александр Владимирович, у него было 3 ученика, которые представили свои работы. И Скопенков Михаил Борисович 2, и Маура Мариане 2 студента представили работы. Это замечательно, что они так активно работают со студентами. Но мы решили в этот раз смотреть на работы именно студентов, которых мы поднимали довольно узко. То есть мы, работая в соавторстве с более senior руководителями и учеными, с людьми с большим научным опытом, у которых уже много статей, мы эти статьи просмотрели, с удовольствием их изучили, но решили вот в этот раз присуждать премию более молодым участникам. И, может быть, это не совсем вероятностной традиции, поскольку известно, вот есть такое распределение студента. Так вот, студент был псевдоним, и писал под этим псевдонимом вполне продвинутый вероятностник. Вот. И несмотря на это, значит, Вильям Гассет, он считал себя студентом, видимо, всю жизнь. Вот. И в этом смысле, наверное, и он бы мог получить премию. Но мы решили все-таки посмотреть на студентов более младших курсов. И вот в результате долгого рассмотрения критерии я сказал примерно какие, а дальше это уже как члены жюри смотрели на работы, что им нравилось больше, что им нравилось меньше. Вот. Члены жюри у нас были, я их сейчас представлю, это был Амир Алиев, Амир, извини, я тебя без отчества сегодня представляю. Вот. Потом был у нас Вадим Евгеньевич Горин. Извини, я тебя с отчеством представляю. И Дмитрий Сергеевич Чукак. Вот. И вот я тоже был член жюри, Константин Михайлович Ханин. Мы смотрели на эти работы, изучали, обсуждали. В общем, нам все это нравилось очень. И в результате долгого обсуждения мы решили выделить две премии двум участникам, которых я сейчас назову. Я не уверен, что они присутствуют здесь. Может быть, очень сильно волнуются и поэтому не присутствуют. А может быть, не так сильно волнуются. Я не знаю, но я не уверен, что они здесь. Ну, мы сейчас проверим это дело. Вот. И, значит, первый участник – это Константин Александрович Афонин. Он получил одну из премий. Он работает его научный руководитель Богачев Владимир Игоревич. И работа, которую он представил, называется «Обобщение теоремы Холлева об аноморфизмах пространств гауссовских мер». Значит, Афонин – это студент 5-го курса мехмата. Вот, и работа посвящена классификации линейных операторов в пространстве мер, зарядов на пространстве РН, линейных операторов, которые сохраняют гауссовские меры, переводят гауссовские меры в гауссовские меры. Вот в этой работе он обобщил теорему Холлева, показав, что классификации достаточно потребует только, чтобы гауссовские распределения одномерные переходили в гауссовские распределения. Этого достаточно для полной классификации таких линейных отображений. И второй главный приз, мы, собственно, два приза не присудили, тут нет первого и второго, оба приза одинаковые, мы присудили два первых приза. Вот. И, значит, вот второй из этих двух главных призов был присужден Бобрину Максиму Сергеевичу, который является студентом 3-го курса факультета математики в Вышке, и его руководителем является Мауро Мариани. И работа посвящена, называется Stability of Gradient Flows in Wasserstein Spaces, устойчивость градиентных потоков в пространствах Вассерштейна. И она посвящена изучению стохастических дифференциальных уравнений с разрывными правыми частями. Вот такие правая часть имеет особенности, и уравнение бы само по себе не имело бы смысла и не имело бы решений, если бы не было случайности добавлено, не был добавлен белый шум, но с добавлением белого шума происходит регуляризация, и эти уравнения имеют точный математический смысл и могут изучаться. Вот это посвящена работа. И нам понравились обе работы, и вот мы хотим поздравить обоих победителей, но поздравить и всех участников конкурса, потому что нам понравились большинство работ поданных, были очень интересные, и мы всех поздравляем и всех благодарим за участие в конкурсе. Это был первый конкурс, и это было важно, чтобы первый раз все это выглядело хорошо и достойно, и так это и выглядело. Еще раз поздравляем победителей Афонина и Бобрина. И вот на этом мое выступление закончено. Но, может быть, кто-то из членов жюри хочет что-то добавить.
Я бы, может быть, добавил пару слов, они такие немножко... Меня слышно?
Да.
Да, они такие немножко банальные. Мне было очень приятно читать работы, ну, как, собственно, Константин уже и сказал, как и всем нам. И я бы хотел сказать, что вот я уже, конечно, довольно стар, но я еще немножко помню время, когда я был студентом, и все эти работы, они строго лучше моих курсовых. Вот я когда читал, у меня был такой критерий для сравнения, и я хочу сказать, что это очень здорово. Еще я хочу добавить такое, ну, очень общее соображение. Вот я тоже вспоминал, когда я был студентом, это, как теперь принято говорить, в России были лихие 90-е, в общем, было такое время достаточно своеобразное, хоть и весьма живое. Ну и, конечно, вот научные стипендии, там какие-то призов никаких не было, но вот какие-то стипендии бывали, и они очень ценились просто, ну, просто в денежном эквиваленте, потому что, в принципе, было всего очень мало. И, конечно, это такая особенность студенческой жизни, потому что, ну, когда ты студент, ну, это везде, во всех странах, совсем не только в России. Вот. Но я бы все-таки хотел сказать не то, что главное участие, а то, что вот когда очень мне было приятно то, что люди занимаются интересными задачами. Это важно. Вот. И я бы хотел как-то сказать, что это очень важная составляющая, то, что вам интересно, и это очень здорово смотреть. Это может быть даже важнее, чем то, что кто-то получил приз, а кто-то не получил приз. Вот, потому что критерии, они каждый раз, как Константин сказал, весовые категории очень разные, и каждый раз нужно как-то устанавливать критерии, это все меняется. Если вы занимаетесь интересными задачами, это уже само по себе большая ценность. Мне было очень приятно видеть, что так и происходит, что в Москве, что в Петербурге.
Ну, значит, Вадим, ты хочешь что-то добавить?
Вадим, Амир, кто-то из вас хочет что-то еще сказать?
Давайте я скажу буквально пару слов. Я хочу тоже присоединиться к поздравлениям всех участников. Мне кажется, замечательно прошел конкурс. Меня особенно порадовало, что у нас было очень большое разнообразие тем. То есть не то, чтобы все работы были посвящены чему-то одному, наоборот, работы были посвящены очень разным задачам, и это замечательно видеть, что в России, в Москве, в Петербурге у нас есть много разных задач, руководители предлагают разные направления, и мне кажется, что такое богатство, его надо использовать. То есть мне кажется, что было бы замечательно, если бы люди, вот, например, присутствующие в этой аудитории, которые подали работы на этот конкурс, они, может быть, отметили имена друг друга вот прям в чате, в зуме, потому что вот все мы – это вот потенциальные коллеги, те люди, которым интересна вероятность, и вообще в развитии математики очень важно общаться друг с другом, получать новые идеи, и я хочу предложить, чтобы вот это вероятностное сообщество студенческое, российское, как-то старалось объединяться. И, в общем, мне кажется, что это важно, чтобы люди больше с друг другом общались. И этот конкурс, надеюсь, поможет такому развитию вероятностного общения. И давайте я на этом закончу. Еще раз всех поздравляю, и победителей, и участников.
Я буквально пару слов скажу. Извиняюсь, что сегодня без видео. Я в составе жюри, меня пригласили как участника индустрии. Я бы хотел сказать, что это вообще не очень простая задача в целом. Когда пишется теоретическая работа, понять, правильно показать какие-то наметки, как это будет дальше в какой-то там в приложениях как-то будет использоваться. Я хочу сказать, и вообще, там тонкая грань, есть серьезный риск в какой-то момент случайно вывалиться из этой теоретической плоскости, и работа будет тогда неинтересна просто с научной точки зрения. И просто хотел сказать, что очень приятно было читать, очень много было работ, которые, вполне оставаясь в этом научном пространстве и доказывая интересные математические результаты, при этом имели определенную проекцию на приложения, которые сейчас есть у разных частей теории вероятности, понятно. Вот, а так было очень приятно, и, конечно, поздравляю, еще раз победителей, и всем хочу сказать, желаю всем участникам и дальнейшего продолжения научных успехов.
Если можно, я скажу еще два слова. Просто может возникнуть вопрос, почему вот первая премия была, первое мероприятие было в области теории вероятности, может быть. Там вообще теория вероятности не всегда рассматривалась, не всюду, как действительно дисциплина математическая. И это очень интересно. Например, во Франции в течение долгого времени было такое отношение, скажем, в 30-е годы, что это не есть, в общем, даже и математика настоящая. И Поль Леви, великий математик вероятности, он даже по этому поводу очень переживал, что истеблишмент французские математические академики, они его не очень признавали. А в России это было не так. В России, может быть, в результате деятельности Андрея Николаевича Колмогорова теория вероятности была, конечно, важная часть математики, всегда воспринималась таким образом, но далеко не всюду в мире это было так. И, скажем, в Америке до сих пор часто теория вероятности бывает в некоторых университетах, на факультетах инженерных, а не на математическом департаменте. Но это все изменилось очень сильно. И теперь теория вероятности – это неотъемлемая часть математики, и она проникает в очень новые области математики и является исключительно важной. И очень развилась, и просто сейчас такой очень хороший период, когда много очень ярких молодых математиков работает в этой области. Даже во Франции сейчас огромное количество молодых математиков идет в теорию вероятности, чего раньше не было. Если мы посмотрим на присуждение филдсовских медалей за последнее время, то много медалей ушли в области, связанной с теорией вероятности, или прямо в теорию вероятности. Можно назвать и Венделина Вернера, и Мартина Хайрера, и Стаса Смирнова, и отчасти даже Андрея Конькова. В общем, явно сместился такой вот шифт произошел в этом направлении, и теория вероятности проникает в очень многие области, которые раньше, может быть, не проникала. Конечно, это очень важная часть математической физики, статической механики, но и в теории представлений, и всюду, во многих областях. То есть я хочу сказать, что вот область, которой вы занимаетесь, это сейчас просто на переднем плане, имеет такую отличную, много энергии, много такого положительного момента, импульса в том, чтобы двигаться вперед. Так что вот, ребята, вы выбрали, с моей точки зрения, очень правильное направление. Прямо двигайтесь и прорывайтесь дальше. Все, спасибо.
Спасибо большое. Конечно, премия бы не состоялась, во-первых, без участников, во-вторых, без наших членов жюри. Я еще раз хочу поблагодарить всех членов жюри за их большую проделанную работу, за готовность помочь и продвинуть область в России, промотивировать дополнительно студентов заниматься задачами в теории вероятности. Но, безусловно, премия бы не получилась без нашего спонсора Siberian Capital. И сегодня с нами есть представитель на этой компании, который, к тому же, является выпускником матфака. И я хочу дать слово нашему спонсору. Сейчас, одну секунду.
Так. Как меня слышно? Здравствуйте.
Да, слышно, слышно.
Да, приветствую всех участников, жюри, организаторов, зрителей. Хочу поблагодарить вас за участие в этой премии. Без вас бы это все не получилось, правда. 4 года назад я еще сам был студентом матфака, как и большинство участников. Вот. Учился, сдавал сессии. И, наверное, как у большого числа ребят, у меня всегда был вопрос, чем же я буду заниматься дальше после университета. Вот. И я пробовал себя в разных направлениях, начиная от анализа МРТ, сделал приложение для распознавания видео, вот, занимался алгоритмическим трейдингом, и вот когда я попробовал себя в трейдинге, я понял, что тут как раз-таки есть темы, которые используются и которые мне нравятся больше всего. В частности, это была как раз теория вероятности, и она была максимально приложена к жизни. То есть я видел результат того, что я делаю, и он был оценен рынком, и я считаю, что это очень честная оценка того, что ты делаешь. Вот. Наша премия – это возможность для студентов, кто занимается теоретической математикой и кто хотел бы себя попробовать в каких-то прикладных вещах. Вот. Она дает шанс сделать первые шаги, вот, и развить какую-то теорию, которую можно потом применить в жизни. В завершение, наверное, хотелось бы еще раз поблагодарить всех, кто участвовал в этой премии, и пожелать вам за то время, пока вы будете учиться в университете, понять, чем же вы действительно хотите заниматься, потому что нужно пробовать, вы там будете совершать ошибки, но пока вы молодые, это вообще никак не страшно. В общем, пробуйте, ошибайтесь. Это нормально, если вам что-то понравится, что-то не понравится. И на матфаке и в других российских университетах, на математических факультетах прекрасная атмосфера для того, чтобы пробовать, потому что если у вас что-то не получится, вам всегда помогут, поддержат, и вы пройдете все трудности вместе. Вот. Спасибо и удачи вам в поиске своего призвания, и спасибо за интересные работы. У меня все.
Спасибо большое. Я еще раз хочу поблагодарить нашего спонсора. Я надеюсь, что это только первый наш опыт, и он, мне кажется, первый блин у нас получился совсем не комом, поэтому мы будем надеяться, что эта премия станет традиционной и ежегодной. А я еще раз тоже поздравлю от лица факультета математики победителей, а тем, кто не выиграл, скажу, что мы ждем их, во-первых, с новых работ, чтобы они снова приняли участие, а во-вторых, тех из вас, кто уже стал взрослеть, мы скоро ждем в качестве членов жюри, взрослых заслуженных специалистов по теории вероятности или, может быть, в качестве как раз представителей компании-спонсора, как вот Александр, который закончил матфак 4 года назад. И, собственно, мы переходим к нашей научной части, завершив торжественно-поздравительную. Костя, я хочу попросить вас представить докладчика.
Да, я представлю. А можно, чтобы показались нам победители свои, ну, как бы вот показали себя?
Как на Оскаре, эмоции давайте, товарищи, отзовитесь.
По-моему, здесь есть и Константин, и Максим, но вот у Максима, может, камеры нет, я вот не вижу.
Да,
у Константина, по-моему, есть камера. Ну,
да, здравствуйте.
Здравствуйте, Максим. Ну, вы же по телефону, наверное, или я не знаю, почему у вас скорее камера.
Я ее убрал.
Ну, хорошо, мы вас поздравляем.
Большое спасибо. Неожиданно.
Ну, неожиданно, но заслуженно. И вот Максим как раз студент 3-го курса. А Константин, вы не покажетесь нам?
Да, я включил камеру. Здравствуйте.
Здравствуйте, Константин. Вот поздравляем вас еще с премией.
Да, это тоже было неожиданно.
Хорошо. Здорово. Хорошо. Вот. Мы, значит, по просьбе Саши, по просьбе спонсоров, и вообще мы считали, что это хорошая идея, мы хотели позвать докладчика, который сделает доклад. Вот, Duncan, I'm starting to say a few words about you. I'm saying that the organizers and everybody thought it's a good idea that this meeting will not be just discussing prizes, but also would contain some mathematical part, and it will be talk, which will be probabilistic talk, an interesting talk, and we thought that it would be a good idea if it is given by young researcher, recent PhD, and Duncan fits the bill very well. He is a very bright young probabilist. He graduated from University of Toronto. He was a graduate student of Balint Virag. He graduated 2 years ago from there, and now he's a postdoctoral fellow. Don't know how his position officially called, but he's at the University of Princeton, working with Sly, and they're doing very interesting work. And I think it's Duncan is. I heard this talk. He gave it before. I think it's an excellent talk, very interesting topic. And I am sure that everybody would enjoy it. And so, Duncan, the floor is yours, and please go ahead and tell us about your work.
Thank you, Kostya, for the very kind introduction. So I'll go ahead and share my screen now. And is it working well?
I think it's good, yes.
Okay, great. Yeah, so I'm going to be talking about some models of infection spread. So all of this is based on joint work with Alan Sly at Princeton. And sort of somewhat coincidentally, we started thinking about a few models of infection spread right around March last year, almost entirely unrelated to the pandemic, but sort of somewhat topical. So what is the basic model? So we're going to, the environment is going to be a sea of particles on a lattice set D, which are performing continuous time random walks. So here's kind of the idea. So each one of these particles, each one of the particles has independent movement. And it performs a continuous time simple random walk. So it'll wait an exponential amount of time, some IID exponential random variable, and then after that amount of time, it will choose one of its neighbors and all with equal probability and move to that neighbor. So particles move in this way. So this is the environment. And then at time 0, or sort of to start the process, we place one extra particle at the origin. So this particle is red, and this particle is going to be infected. So we think of the blue particles as susceptible, and the red particle is infected, and it's going to do exactly the same thing as the blue particle. So it's just going to perform a random walk on the lattice. And the rule for how this process evolves is that every time an infected particle meets a susceptible particle, that susceptible particle will also become infected. So you know, in kind of this example here, maybe the red infected initial particle will take a few steps, and it'll take enough steps that it'll sort of hit this neighboring susceptible particle before that susceptible particle is moved, perhaps. And then that susceptible particle will become infected. And then now we'll have 2 infected particles, and then they can go around and start infecting more and more particles in this way. Okay, so I'll just say a few more things about this. So the first is, you know, this second rule here for how the process works is basically what I just said. So when susceptible meets infected, susceptible becomes infected. And so for this reason, we often call this an FI model. So this terminology is kind of common in the epidemiology literature, and people in interacting particle systems kind of stole this for thinking about this. And we're going to, the one thing I haven't said is what is your initial distribution of particles? So basically, just to simplify some of the analysis, we're going to start with the particles in equilibrium. So what does this mean? So imagine you do the following thing. I put one particle at every lattice site, and then I let all of these particles perform independent random walks, and I just see how the distribution of particles evolves as time goes to infinity. So what happens is as time goes to infinity, this converges to a stationary distribution. And what this is you'll still see, what you'll see is an independent number of particles at every site. And the number of particles will follow a Poisson distribution. So this is called a Poisson distribution on ZD. And in the example I gave, so if you start with one particle at every site, this is like a density 1 process. So then you'll have all of your Poisson processes in this equilibrium will have mean 1. You could also put Poisson random variables at every site with mean rho for some rho. So that will be the density rho equilibrium measure. So we're just going to start with some equilibrium measure in this way. Okay. So here's some simulations of how this process grows. So these are 4 equal time steps. And what you can see is this infection kind of spreading out from the center. And well, it's probably not completely obvious from the picture, but this is linear spread. And you see sort of a shape start to form. You see a few particles infected at the start, and then they kind of spread further and further. And if we think a little bit about this, what's causing the infection to move forward is not so much the movement of the random walks, but it's the collisions between the particles. So the random walks in time t, you're going to expect them to move like distance square root of t, whereas our infection is moving at linear speed, so it's moving much faster than the random walks. So typically, sort of in this view, the random walks are kind of stationary from the point of view of the infection, and this front of the infection is passing through new particles, and it's the collisions between the particles which cause more and more particles to get infected and the sort of infected region to grow. Okay. So I'll mention a few other interpretations for this. So this is not a particularly realistic model of infection spread, but you know, you start to see some interesting features, and it's interesting to study theoretically. And here's some other interpretations. So one is you can think of this sort of a general model for a propagating front. So you have sort of this infection front, which has this kind of complex dynamics where on the one side you have a moving environment that it's moving into, which is the sea of susceptible particles. And the front itself is also moving because the infected particles in the front can move back and forth. So it's sort of a general model for a front propagation. And you can have a couple of other interpretations. I think that the second one, which is a chemical reaction, this is a little bit more natural. So the idea is you have two species of particles. You have A particles and you have B particles. And every time an A particle meets a B particle, they'll sort of perform a chemical reaction. And you'll have a transition between an A particle and a B particle to two B particles. So it's kind of a toy model for a reaction. You can also, sometimes this is considered as a rumor for information spread or rumor spread. So the idea is that one particle at the origin knows some information or knows a rumor and wants to spread it to all of the neighboring particles. So every time it meets a particle, it's going to tell them the rumor. And this rumor is very exciting. So every particle will want to spread this rumor. So that's the idea there. Okay, so moving back to this this idea of working with an infection model. If you're working with an infection model, sort of the natural thing to do is introduce the possibility of recovering from the infection. So we're going to introduce a recovery rate for this infection. So what does this mean? So every time a particle gets infected, it's going to have, it's only going to stay infected for some amount of time. And the amount of time that it stays infected for is going to be an independent exponential random variable with parameter lambda. So it's going to have, it's going to be infected for, on average, 1 over lambda amount of time. So lambda, this parameter, is the recovery rate. So if lambda is very large, then particles don't stay infected for very long, they'll recover quickly. If lambda is small, then particles will sort of stay infected for a very long time and maybe have a chance to infect many other particles. Okay, so once you introduce a recovery rate, then you have two versions of the model. So there are, I mean, you can have more, but we're just going to consider two. So the first model you could consider would be, okay, after they recover from the infection, they just go back to being susceptible particles. Okay, and they can become reinfected over and over again, for example. The other version of the model would be where particles become immune after they recover from the infection. So this is called, so this first one's called the SIS model because they go S to I back to S. The second version of the model is called the SIR model because they go from susceptible to infected to removed from the process. So once they're immune, the right way to think about these particles is that, you know, they're no longer participating in the dynamics. They're sort of, you know, no other particles see them or care about their behavior. So for all intents and purposes, we're just going to remove them from the process completely. Okay, so one thing you expect to happen is that if the recovery rate is very small, so if particles typically stay infected for a long time, then this model behaves a little bit like, then this model should kind of behave like what happens when particles aren't able to recover. So this is an example of this is a simulation of the SIR model with a small recovery rate. So in the picture, you can see that the infection is spreading. So again, the red particles are the infected ones. So the infection is still spreading. It looks like it's spreading linearly, just like in the case of where we had no possibility of recovery. But The other thing that you see, which is different from the SI model, is you see a region in the center, which doesn't seem to have very many infected particles. So in this picture, all of the removed particles are genuinely just removed from the picture, so we haven't shown them. And that's what you're seeing in the center of this linearly growing ball, is that in the center, most of your particles are just completely removed. And so what you really expect to see is kind of a ring of infection traveling outwards. And the thickness of this ring is going to depend on the recovery rate. So that's kind of what the simulations are suggesting. Okay, so let's try and say something mathematically. So these kind of models were first studied by Keston and Siderovicius. So I think they started studying them around 20 years ago. And they started with the simplest variant, which is just this SI model. And they proved the following thing. So I'm going to, I'll let CT be the set of sites in ZD, which have been visited by an infected particle by time t. So this is kind of a proxy for this infected set. So what they showed is the following, that if you take CT, so we expect this CT to be growing linearly. So if we want to understand, the long time behavior, the right thing to do is going to be to rescale this set by t. So if they take this set CT, they rescale the set by t, then they showed that it converges to a deterministic compact set K. So it converges almost surely to some deterministic compact set K. So if you, it's not super important what the type of convergence is here, but this would sort of be almost sure convergence in the Hausdorff topology on closed sets, if you want to say something more technical. But it's not very important. Okay, and this compact set K is, you can say a few things about it, but it really, this is an abstract field, so you can't say too much about it. But we do know that it contains a ball around the origin and of some radius epsilon, and you can also say it's contained in some large ball of some radius c, where you could say what c is, or you can sort of quantify c based on a few parameters of the process, or the density of the process. Okay, so in this world of probability, this is what's called the shape theorem. So you have a sort of a geometric probabilistic model, and you want to prove something like this. And it's in this world, it's the analog of a law of large numbers. Okay, and so just like if you in the first probability class you take, the law of large numbers is probably, I don't know, usually it's maybe once you maybe have some foundations out of the way, it's like the first theorem you learn how to prove. Okay, and with these geometric probability models, the idea is, the first thing you should be able to prove is also a shape theorem. Okay, so in some sense, this is kind of the very beginning of the exploration. And for certain models, so for some models like first passage percolation, shape theorems are well understood. It's kind of, there's a well understood way of getting there. And this is, again, in first passage percolation, sort of a different geometric model that's a little bit easier to understand. This one, it's kind of easy to show these things. Here, in contrast to sort of law of large numbers and some other more tractable geometric models, the shape theorem is very hard. So this work of Keston and Siderovicius, they combined a bunch of different ideas from percolation theory and the theory of branching random walks, and this sort of this long 100-page thing spanning a couple of papers, which culminates in this Annals of Math paper where they prove this. So it really is, the point of this digression is really to say this is quite a difficult model to study. Very, very little is known about it. It's remarkable that they were able to prove this much. On the sort of spectrum of probabilistic models, this is very hard to say things about. There's no integrable structure. There's very little even sort of basic combinatorial structure there. Okay, so the next thing they turned to was the SIS model. Okay, so for the SIS model, the way I think about these models is you have SI, you have SIS, and you have SIR. And SI is the easiest to study, but there's somehow the least amount of stuff going on there. And in this SIS and this SIR model, that's where you can start to see some more interesting phenomena. So the first thing that you expect to see is that the behavior of the SIS model should depend on the recovery rate. So if the recovery rate is very small, then what you expect is that it looks a little bit like the SI model, that the infection grows linearly and the infection should survive forever, at least with some probability. But if the recovery rate is very large, then what you expect is that the process just dies out. And that's what Keston and Sidorevicius. So they showed that for every density rho and for every dimension d, so I've split this into two theorems. I'll say the first one. They show that there's a critical lambda such that if your recovery rate is smaller than this critical lambda, then the infection survives with some probability, and that if it's larger than this critical lambda, then your infection will just die out. And the way that they showed this is that they proved that the survival probability is monotone in lambda. Okay. So this is part one of the theorem. In some sense, this is actually quite easy. So how do you typically show monotonicity of these sorts of things? What you want to do is take a version of the process with one recovery rate and a version of the process with another recovery rate. So have recovery rate, say, lambda 1 less than the recovery rate lambda 2. And you want to realize these two versions on the same probability space. So we're going to couple these two versions together in such a way that the set of infected particles in one of the processes always dominates the set of infected particles in the other process. So you can do this, and sort of the most natural coupling works here. Sort of, if you've been thinking about these things for a while, there's one really natural coupling, which shows that when you couple these two things together, that the process with the higher recovery rate is always going to have fewer infected particles than the process with the lower recovery rate. So in particular, if the higher recovery rate process survives, then so does the lower recovery rate process. So this is a nice monotonicity feature of the model. And the second thing, and this is really the non-trivial part of this SIS theorem, is that this critical parameter is non-trivial. So it's not equal to 0 and it's not equal to infinity. So these two regimes genuinely actually exist. You will see survival, and you will see sort of a regime where the infection almost surely dies out. Okay, so this is what Keston and Sidorevicius did, and there are many questions that are left beyond this. So the one that I'm mostly going to talk about is what happens with this SIR model. Okay, what can you say in this context? And another question is about the growth of this front. So one thing we really care about is understanding this propagating front. We want to show that it propagates linearly. So the question is, do the models grow at linear speed if they survive forever? And a much more, in some sense, a much more ambitious question would be to get a shape theorem. So to mirror this shape theorem for the SI model, can you get this for, say, the SIR model and the SIS model? So what would a shape theorem look like in this context? Well, there's always going to be some chance that the process just dies out. So you'd want to say that if the process survives forever, then your infected front converges to some limiting shape after you rescale. And when it comes to the SIR model, things get a bit more complicated. So here are two kind of key difficulties with this model, which we're going to need to overcome if we want to understand this. So the first is you can't really think of this system as being in equilibrium. So here's something you can do with both the SI model and the SIS model. So you can take your particles and you can forget about their labels. So you can forget about whether they're labeled S or I. And in this case, what you see is just particles performing independent random walks and evolving. And because you started out at an equilibrium distribution, they always stay in equilibrium. And this means that this allows you to do some analysis of the process, which is kind of nice. This is not the case with the SIR model. So it doesn't really gain you any traction to lump in these recovered particles with the susceptible and infected ones. So you really have to think of these recovered particles as being completely removed from the process. So in this sense, there's no natural way of thinking of this process as being in equilibrium, and this causes some difficulties in the analysis for sure. Another thing which is very, another thing is there's no monotonicity in the SIR model. So this theorem here for the SI model, where I said, there's some natural way of coupling processes with different recovery rates. You can't do this for the SIR model. You can try it, and I tried it. So both Alan and I thought about this, and the various constructions that you try just don't work. So of course we still believe that there is, some monotonicity in these parameters, but we don't know how to prove it. So this really means that, for example, you can't establish the existence of a critical lambda in the context of the SIR model. Okay. So what can you say? So there are a few things that are kind of easy to say in the SIR model. At least they're a bit easier to say. So the first thing you can show is the following. So for any density and any dimension, if your recovery rate is large enough, so if it's larger than some lambda plus, then you can say that the infection dies out. So this is not too hard. And one way you can think of this is if you go back to the SIS theorem, if the particles are becoming susceptible, what Keston and Sidorowicz showed is that if the particles become susceptible after they recover from the infection, then if your recovery rate is large enough, the infection still dies out. And becoming immune is definitely going to be better for killing off the infection than becoming susceptible. So that's one way you can see that this would have to hold. And in fact, this theorem is not too difficult to prove. It's I don't want to take credit for these theorems. I think that these are more or less folklore. This one is based on a fairly straightforward martingale argument. For this second theorem, the other thing you can say is, so this concerns dimensions greater than or equal to 2. For the second theorem, you can say that in dimension 1, the infection will always die out. Okay. So this again, it's harder than this first theorem, but it's not too difficult to develop an argument which shows that definitely this infection will die out regardless of the recovery rate, regardless of the density. So the thing that's interesting here is in dimension 2 and higher, there should be another regime where the infection has a positive probability of surviving. And this is really where I think things get interesting. So this is what I mostly want to talk about. Okay, so this is our main theorem. So for every density and every dimension, there exists a lambda minus such that if your recovery rate is smaller than this lambda minus, then there's a positive probability event where the infection survives through. So I'm going to say a little bit more about this event A, but let me first mention this thing where we say that it's positive probability. So you might hope, or you might think at first, well, could you say that the event A has probability 1? And the answer is that the event A will never have probability 1. There's always a chance that this initial infected particle will just die out before it meets any other particle. It will recover from the infection rather before it meets any other particles. Okay, so you can never say that A has probability 1. Maybe you could get bounds on the probability of A, but that's kind of a more nuanced question. Okay. So I think what's really interesting is how we can establish that the infection survives forever. So not only on this event A does the infection survive forever, but you can say a bit more. So the first is that the infection will grow with linear speed. So we have this picture of the infected particles looking like they form a ring extending outwards with linear speed. And this is what we can show. So I'm going to let CT be the set of sites containing an infected particle at time t. So there are constants, C1 less than C2. Again, these constants are going to depend on all of the parameters, and I'm not going to say what they would be explicitly but you can show that CT is contained in the annulus of inner radius C1 and outer radius C2. So you see this sort of ring growing outwards, this infected ring. Okay. And so what's happening inside the ring? So in this ball of radius C1, you no longer see any infected particles, which is great. The infection is never going to return to this area. And what this is you've established a herd immunity region. Okay. So there are two types of herd immunity that can occur in this model. There's like a trivial herd immunity and a non-trivial one. So what would the trivial herd immunity be? Trivial herd immunity would say that in this region, every particle was previously infected. And so you only see recovered particles in this region. So this is kind of completely trivial. Or, another interpretation of the model is if particles recovering means that particles die off, then this is not so much a herd immunity region as just a region that the infection has completely wiped out. Okay, so that would be a trivial herd immunity region. But what actually happens is you get a non-trivial herd immunity region here. So not only do you see a bunch of particles here which have recovered from the infection, but you also see a positive density of susceptible particles. So you sort of see some very small density of susceptible particles. Again, in the course of the proof, the actual density we get is so incredibly minuscule. It's not really worth trying to keep track of what this C3 would actually be. But there is some density of susceptible particles. There will always be particles that never get infected on this event A. So this is the picture, and funnily enough, because all of the results are taking place as time tends to infinity. So these are Allen simulations, and I know this one took him a lot of tweaking to kind of get the parameters and the time frames right to actually get a picture that looks like the theorem. So you see this ring. It's kind of, even this picture is a bit funny, right? Because the ring has this funny, concave region here, which really shouldn't happen in this model. It's just some small time effect. And inside the ring, you do see this very low density sea of susceptible particles that kind of squeeze through your infection front. Okay, so let's try and refine our understanding at the front just a little bit. Okay. So what's a way to think about how the front passes through a region? So when you can say, okay, the first time the front is at a region, we'll call that SX. That's going to be the first time you see an infected particle at some site X. Call TX the final time you see an infected particle at the site X. Okay. So what this first part of the theorem is saying is that if you look at the difference between TX and SX, so this is like the amount of time the infection spends at site X. If you average this over a ball of radius R and sort of take R to infinity, then this is order 1. Okay, so it's bounded above by some constant. On this event on this event A where the infection survives forever. So the front is spending roughly order 1 amount of time at every site. Okay, and this is not getting worse. So the front is not sort of spending more time at sites that are further away from the origin because of some accumulation of infected particles. And we kind of have a counterpoint to this theorem, which says that there's also, you can also ask, okay, what's the worst case scenario for this TX minus SX? And the worst case scenario is when in a ball of radius R, the worst value of TX minus SX is like a constant times log R to some very slowly growing power. Okay. So how to read this second part of the theorem? One, a constant times log R is a pretty good bound that tells you that if it was a constant times log R, that would tell you that the amount of time you spend at each site, or the amount of time the infection spends at each site has an exponential tail, which is very good decay. We have this triple log correction in the exponent. The way you should read that is that's a sign that there's some technical analysis at some point in the proof. It's certainly not a physical feature of the model. It's a feature of the analysis. Okay, So what's the idea of this front theorem? So if we spend order 1 amount of time at every site, and we know our front is moving linearly, that means the thickness of our front is order 1. And that's what this picture is. So this is my, the sketch of what this is telling you about the front. So here, red is infected, blue is susceptible, and black is removed. And on the right side, I just genuinely removed these black particles from the process. And what this picture gives is that it shows that so what's the theorem saying? It's saying that on either side of the front, you have a supercritical regime on the one side of the front, where you basically see a fresh set of susceptible particles where your infection can move forward into. And on the other side, you see very few particles, because most of the particles have been removed. And so that's sort of a subcritical regime. So you have these supercritical and subcritical regimes living side by side. And on the one side, basically the infection will die off exponentially fast. And on the other side, it's going to propagate. And the other thing is the front is moving forward, right? The front is moving forward into this sea of fresh susceptible particles. But the random walks themselves are not moving. They don't have a bias in any direction. So the reason that the front is moving forward is because of this difference in the density of particles on either side. So you have this dramatic density difference, and this is what's causing the front to appear like it's moving forward, even though the random walks themselves are, just diffusing. Okay, so let's say a bit about the proofs. So here's the most basic thing you can think about with this model. So what are you trying to, why should you imagine that this is moving forward at linear speed? So roughly you should think that, okay, the infection spreads out at linear speed, and just ahead of the front of this infection, you see a lot of susceptible particles. You kind of see a fresh, independent set of random walks, and so you'll see some collisions there, and the front is going to push forward into this set of random walks. Okay, and it'll kind of keep pushing forward. Okay, and because it's moving at linear speed, for some reasons that I'll discuss in a second, roughly you see kind of a good density of susceptible particles always in front of the front. Okay. So what if we're trying to build on this heuristic, what we should do is we should try and understand the environment of particles just ahead of the front. So that's what this picture is showing. So time is going up here and space is going back and forth. It's kind of a one-dimensional picture, if you will. And the black trajectories here, think of these as all of the trajectories of infected particles. So some of these trajectories kind of stop short because infected particles recover. Okay. So say I have access to all of the information in this black tree. You can ask, given this black tree, what is the environment just ahead of the front? So a good way to think about this is to think, okay, what sort of trajectories would susceptible particles just ahead of the front be allowed to have? Okay, so here's two trajectories. The first one is blue, say. So this blue trajectory is allowed, right? So if this blue particle started here and followed its trajectory, it would never encounter an infected particle, so this trajectory would be allowed. But on the other hand, the red trajectory is not allowed, right? Because if the red trajectory were to occur here, then at this time, the red particle would have become infected. So it would have become infected. And so at this point, it's either going to be infected or it's going to be removed from the process completely. So this red trajectory is not allowed. Okay. And so the idea is, well, what does the environment look like just ahead of the front? Well, it's going to look like basically, if this black tree wasn't there, if you didn't need to avoid the black tree, then it would just look like this equilibrium measure. It would just, you would just see Poisson many particles at every site. Here, you're still going to see Poisson many particles, but it's going to be, the density is going to be sort of cut by the probability that the trajectory going backwards hit this infected tree. So let's say this with a slightly more formal language. So I'm going to let ft be the sigma algebra generated by all trajectories of infected particles up to time t. So this is this black infection tree. And I'm going to let AT be the set of infected sites at time t. So this is just some information contained in ft. So this is this ft will contain all of the sets AS for S less than or equal to t. It will contain all infected sites at times prior to t. So what you can show, what I was roughly explaining previously, is if you look at the expected number of susceptible particles at a site X, given this information about the infected trajectories, then what this is this is just the density of your process rho times the probability that a random walk moving backwards always avoided this black tree. So here, XS is a random walk moving backwards in time, started with the condition XT equals X. Okay. So this point is a special feature of the fact that we had a Poisson initial condition. So some version of this would exist for other initial conditions, but the fact that it's so nice that it's a Poisson initial condition feature. The final point is that, again, because of the special Poisson initial condition, the number of particles at different sites is still independent, it's still Poisson distributed. So you have a really good understanding of the environment just ahead of this front. Okay, so now how can we use this information? So say we knew that the front was moving forward at linear speed. So if we know the front is moving forward linearly, then what is this probability? This is basically asking for the probability that a random walk moving backwards avoids a cone. Okay. But because a random walk moves diffusively, it's moving like square root of t in time t, whereas the cone is moving linearly, it's easy, or it's, if you can avoid the cone up to say, time 10,000, then you can typically avoid the cone forever. So the point is this probability is bounded below in t. Okay, so if we know the front is moving linearly, then this probability is bounded below in t. And so we always have sort of a positive density of particles sitting just ahead of the front. So that's the idea. If we know the front is moving linearly, we'll always see a fresh set of susceptible particles. And if we see a fresh set, then that should keep the front moving forward linearly, because we'll be able to keep sort of propagating forward. Now, there's an issue with this, which is that because of kind of rare events, there will be places where the front collapses and stops moving linearly. So a couple of events you could imagine. One would be, say, one portion of this front, which we know is sort of only order 1 thickness, say all of the particles in that portion simultaneously recover because of a large deviation event. So that's going to cause the front to collapse and not move linearly at that point. Another thing that could happen would be the front moves into a region where, again, because of sort of a large deviation event, we just happen to see very few particles there. And so it can no longer move linearly through. And this is an issue because the moment it's not moving linearly, then this probability no longer satisfies a nice lower bound. So this whole scheme would start to collapse on itself. Okay. So the idea is, if we want to show that this process, survives forever and moves forward at linear speed, we want a construction related to the process, which is going to take into account where the front moves slowly. Okay, so it should take into account where the front moves slowly. That's going to be key. And it's also, it's also going to need to have some independent structure, which is going to allow us to actually do analysis on it. So let's try and figure out what this construction is going to be. And the idea is going to be to replace this somewhat complicated model, this complicated interacting particle system where you have lots of moving particles, replace it with something a little bit simpler. So here's our first attempt. We're just going to define a coloring process in the following way. So we're going to do some sort of coarse screening procedure, where what we do is you take the lattice ZD. Okay, in this case, I'm really thinking of this as working on the plane here. So you're going to take the plane Z2, divide it up into boxes. Okay, so in this case, I drew 2 by 2 boxes, and we're going to color the boxes every time an infected particle enters that box. Okay. So we're going to color the boxes red. So this is maybe the box of the origin. This one started out being colored red, and then an infected particle moved to this one moved to this one, one moved to this one moved to this one. They all colored red. Okay. And so we could keep coloring things red in this way. And this would just keep track of the front. But what's going to be more useful for us is we need to understand where the front moves slowly, or where maybe it collapses because the infection dies off. So what we're going to do is, if we move into a region where for some reason or other we are forced to move slowly, or all of the particles recover in that region, we're going to color that spot blue. So red squares are now going to be places where the front is kind of able to move forward at a linear speed, and blue squares are going to be places where the front is moving slowly. But the key idea is to keep the entire coloring process moving forward at linear speed, so that the number of particles we see every time we encounter a new box is always sort of has a reasonable density. So even in these in this blue area, when we color things blue, that's going to be a signal that, okay, rather than moving the front forward, we're just going to artificially move the coloring process forward. And so the blue is going to kind of represent a sort of ghost front. So let me say this, slightly more slowly. So we have the idea is that, we have a coloring process which is going to color blocks as the front roughly moves forward. Every time we encounter a block, you're going to see some, independent batch of randomness coming from the particles in the block and the recovery times associated to the particles in that block. So we're going to start by looking at the local randomness and calling a box a blue seed if we look at that local randomness coming from a block and seeing that it might cause the infection to spread really slowly. So we'll call those boxes blue seeds. And so this coloring process will just be red. It'll keep moving forward as a red process until it encounters a blue seed. And then it's going to color that box blue. And then blue seeds are going to be able to grow as well just after a fixed waiting time. And this is going to keep the whole coloring process moving forward at linear speed. Okay, so this might not seem like a huge simplification, but it really is a much easier process to analyze what we've done. The idea is, before we had particles, they were moving all around. Now we just have a process which is growing. It has two competing growth processes. It has a red process, it has a blue process, but these things are, they're still just growing processes. So the idea is going to be, we want to show that these regions that get taken by the blue part of the process are rare. So basically you see these slow parts of the front, you see these blue areas, but they're so rare that you can still conclude that the whole process is moving forward very quickly. That's what we're going to try and do. So that's the goal, analyze the process. So let's think, if we didn't have the blue process, this whole thing looks a little bit like a kind of well-known probabilistic model called the Eden model, or first passage percolation. So the Eden model is something you might be familiar with. It's more famous than the models I'm talking about. So the idea is you have an aggregate set of sites in ZD, which we'll call RT. And at every time t, RT is just going to look at all its neighbors, and it's going to add all of these neighbors independently at rate 1. So what I mean by this is, to each one of these neighbors, you're going to associate an independent exponential random variable of mean 1. And after that exponential waiting time, you'll just add that neighbor. Okay. So you add that neighbor and kind of tick this whole process forward. So once you've added one neighbor, then you start this whole thing again. You look at all of the neighbors, IIG exponential clocks, move forward. So this would be like the red process without any of these blue seeds. And this looks a bit up to some details. This looks a bit like this is actually precisely a growing ball in a random metric. So what's happening here? You can define metric on ZD, which is this function d of xy, where the distance from x to y is going to be the particular weighted graph distance. So it's going to be the minimal weight of a path in this path in the graph ZD, where you put edge weights, which will define the weight of your path. So you're going to put edge weights, which are just IID exponential random variables. Okay. So this aggregate RT is actually a growing ball in this metric. Okay, and it makes it, it's maybe not completely clear from what I said, but not too difficult to show that this is true. And because you have this metric connection, it makes the even model much more, it's still a difficult model to analyze, but it's easier to analyze than this sort of infection spread model that I've been talking about so far. So our percolation process is a bit like the even model, except it has the following caveat. So it's going to encounter obstacles. Okay, it encounters these blue seed obstacles. So it's still like a growing ball in a metric. But what happens is it encounters a blue seed. The blue seed will try and compete with the process and maybe take a little chunk away from the red process. And then maybe it encounters a larger group of blue seeds, which can maybe work in tandem to be able to cut off a larger portion of the process from the red guy. So the outer edge of the red process is going to actually be our front in the original infection model. And these blue parts of the process are going to represent places where the front collapsed, either because the particles weren't there or because the infection, simultaneously recovered very quickly, something like that. Okay. So this process is very similar. The process that we define to analyze this infection model is very similar to a process defined by Sidervicius and Stauffer. And so what Sidervicius and Stauffer showed for their version of the process is that if your density of blue seeds is really low and the dimension is greater than or equal to 2, then this red process will survive forever with positive probability, and it will just enclose a few small blue components. And they basically did this with something that looks a little bit like this diagram. They used a multi-scale analysis. So what they did is they grouped blue seeds into different scale clusters based on sort of how many neighbors they had nearby. And they performed this sort of analysis. Actually, their process is a bit more complicated than ours, but we can kind of bootstrap off of their analysis, simplify some of the ideas, and it works in our context. Okay, so that's the basic idea that's my rough sketch of the main difficulty in the proof, which is showing that this process may survive forever. This infection process may survive forever and move at linear speed. Maybe one more thing before I move on is, in this competing red-blue setup, you could have a situation where your initial red process is just surrounded by blue seeds. Okay, and in that case, the red process won't be able to spread. And this, in some sense, corresponds to the infection dying off instantly. And so that's why in this theorem here, you can only say that the red process survives forever with positive probability. Okay. Can't say that it survives forever with probability 1. Okay, so I'll maybe in the next 5 minutes or so, I'll talk about a few variations. So one kind of nice variation is, which is fairly natural, is okay, just consider the SI model. We'll keep things simple. We won't have any recovery, but change the speed when the particles become infected. So I think this is particularly natural from the point of view of thinking about chemical reactions. So you'll have 2 types of particles. You're going to diffuse at different rates, right? So what's difficult about this process to analyze is, again, it has this issue that it's not in equilibrium. So because your particles now move at different rates, whether they're susceptible or infected, even if you forget about the S or I labels, you won't just see an equilibrium movement of C of random walk. So you'll now see random walks moving at different speeds, which throws things out of equilibrium. And in particular, it means that there's no monotonicity in this model in the density parameter. So this lambda should say rho. This is the density parameter. So it's kind of some extra complications, which meant that Siderovicius and Keston, when they were thinking about this, they weren't able to say very much about this case where the speeds are different. But what we realized is that sort of a version of our techniques, so sort of a few extra ideas thrown in, can prove interesting things about this case where the infection rates are different. So this particular theorem answers an open question from the Keston and Siderovicius paper, which says that the following. So consider the SI model with arbitrary speeds and any dimension. And I'm going to let CT be the set of sites that have been visited by an infected particle by time t. So then you can say that this set CT is growing linearly. So it's always contained in some big ball, and it always contains some small ball as long as t is large enough. So these are balls that are growing in t. And again, it's the kind of thing where these constants C1 and C2 are not explicit and will depend on all the parameters of your process. So they'll depend on the density, they'll depend on D, they'll depend on DI, and they'll depend on DS. Okay, so this might feel like a bit of a technical extension, but there is something, some genuine phenomena to explore here, which is, well, how does the growth of CT depend on DS and DI? And this is something that, that physicists have thought about, and they came up with the following, conjecture. So this is supported from some ideas in the physics literature, which is that this set CT should grow, and it should grow, and it should have some limiting speed and some limiting shape, for example. And their belief is that these only depend on the dimension, the density of your process, and the rate of and the speed of the infected particles. They don't actually depend on the speed of the susceptible particles. So this is I think it's a good open problem. I don't know. We haven't thought about it too much. But the question is this true? Prove or disprove that the growth of CT, so I stated it here as the limit shape, but just prove or disprove that the growth of this set CT does or does not depend on the speed, the diffusion rate of these susceptible particles. Okay, so then the last thing is, one more generalization is, okay, this theorem concerns positive speeds. What happens if you take one of the speeds to 0? And you get two really interesting models here. So the first is called the frog model. So this is what happens when you set ds equal to 0. So now you have susceptible particles which are still, you have an infected frog, which is going to hop around until it lands on a sleeping susceptible frog. And then every time it lands on a frog, well, frog lands on another frog, it's going to irritate that frog, wake it up, and it's going to start hopping as well. So that's why this thing is called the frog model. So you'll see a bunch of frogs hopping, and every time they land on other frogs, they'll wake up those frogs, which will start to hop. So this is actually a really well-studied model. Lots is known about it. It's somehow, or a decent amount is known about it. Somehow the structure is quite a bit simpler here. So this is somehow, setting one of the speeds to 0 really simplifies the setup. Now you could try setting the other speed to 0, which would be setting the infected speed to 0 and keeping the susceptible particles moving. So when you do this, you need to make a small change to the setup. What you want to do is say that, okay, basically now what you're going to have is you're going to have a growing aggregate of fixed infected particles in the center. And for this aggregate to grow, you shouldn't have susceptible particles move. So you shouldn't have susceptible particles stop moving when they land on the aggregate, but rather when they land adjacent to the aggregate. So when you do this, this is called multi-particle diffusion limited aggregation. Kind of has this funny name. But you get really cool pictures. So this is a high density version of the process, and this is a low density version of the process. And what you see is that the aggregate grows outward and has a, it has sort of a limit shape at a coarse scale, but at a fine scale, you see these dendritic growths. So this is kind of this is a model for all sorts of things. For example, you can think of it as a model for lichen growth or electrodeposition, things like that. In the regime where you take the density of the particles all the way down to 0, this converges to an even more well-known model called just diffusion limited aggregation. So this is sort of a multi-particle version because we have a sea of particles rather than sort of one particle coming in at a time. Almost nothing is known about these models. So that you can, some of the techniques that I mentioned here were actually employed by Siderovicius and Stauffer to say a little bit, to say something very small about this really high density regime. But for the most part, almost nothing is known, though there's all sorts of cool things that should be expected to happen for this diffusion limited aggregation. Okay, I will go ahead and stop there.
Thank you very much, Duncan. Thank you. Please, do people have any questions?
Duncan, can I ask you, so you had these in the first part of your talk, you have these kind of growing rings for the infection front. Were those really circles or they were not quite circles?
So they're not, nothing in here is supposed to be a circle, right? So it should be like,
yeah, like this one, like for example.
Like this one here, yeah.
Yeah.
So yeah, it shouldn't be a circle. It should, you know, it should be some limit shape. I think it's possible that maybe in very high dimensions you could show that this is not a circle, or not, you know, not a sphere in very high dimensions. But in low dimensions, the question of actually determining whether or not this is a sphere, I think, will be very hard.
But this one, like this particular image, it even looks kind of asymmetric. Is it? Is it just because it's?
Yeah. So the limit shape. So maybe if I go to this, like this limit shape K has lattice symmetries, right? So it's you know, what's known about this K? Well, basically nothing. But you can say that, you know, it's connected, or like, okay, so it's going to be a simply connected convex shape with lattice symmetries around the origin, but that's all you can say. You know, the situation with this K is it's kind of similar to the situation first passage percolation. Very little is known about the limit shape, but certainly I wouldn't expect that it's a circle or any nice shape.
So there are even no conjectures like what it should be.
No, I mean, you can kind of see, I think like one thing that's kind of clear in these models is like this. You know,
yeah, that looks quite weird.
Yeah, so I think the issue here, I mean, you know, I'm not going to claim that Alan was, when he was doing his simulations, he wasn't aiming for sort of something more than just trying to get a picture, but the time here is so small that this is, you know, this concave part here certainly doesn't exist in a limit.
Okay.
All right, any other questions? Maybe I ask one question. So you mentioned this open problem to prove that the limit shape, which is, we don't know whether it exists or not, but you suspect it exists, doesn't depend on ds, right? But can you prove that the estimate, I mean, this linear growth of this ring, linear growth coefficients do not depend on ds? I mean, not the shape.
So I mean, this is, I think this is, yeah, so I like the reason this open problem is maybe still accessible without knowing the limit shape would be if you could show something like this. Like, you know, you could try and say, okay, if you take the speed of susceptible particles down to 0, or if you take it off to infinity, can you say that this forces some change in the growth of this set? And we don't know how to do this, basically. I mean, so one, you can, I mean, the simplest setting to try and attack this would be even try and understand this in dimension 1. So in dimension 1, everything should be pretty simple, right? You should be able to say, like, in most models, you should be able to say almost everything in dimension 1. And maybe, and this is where I would try and tackle this sort of problem, but I don't know if it, like, you know, from early thinking, it was not clear one way or the other. There's no, it's certainly nothing happens like, it's not the case that if you take it's not the case that if you take the susceptible particle speed to infinity, then the growth rate tends to infinity. That's the sort of thing which would, you know, obviously contradict or would obviously solve that open problem. But that certainly doesn't happen.
And I have another question. So in statistical mechanics, there is a notion, sometimes shape theorems appears in the context of droplets of one phase inside the other, and then the limiting shape usually is solution of certain variational problem involving surface tension on a boundary. And so is there anything like of this type possible here, that there is a variational problem which is for which the limiting shape is a solution?
I mean, so I guess the closest model that I know of where something like this is kind of known is there's like for last passage percolation, you know, you can say that the limiting shape solves some variational problem. And my feeling with first passage percolation, I guess I don't think it's been proven that such a thing is true, but it should, you know, heuristically, it should be the same. And this model, at the level of the limit shape, it should behave a little bit like first passage and last passage percolation. So my guess is, you know, there should be some description like that. But it's, you know, it's really quite science fiction. I mean, this, yeah, I certainly it's, I wouldn't know where to start for trying to prove something like that.
I see. I understand. Well, are there any other questions? If not, then I suggest we thank Duncan again. And thank you very much. And I think it was a very interesting talk with a lot of problems which are probably challenging, but quite interesting and looking simple to start thinking about, at least.
Simple to start thinking about, but I think everything here was very hard. There was nothing, I don't think there was, the kind of thing that is, you know, maybe the things that are kind of accessible is like understanding things in dimension one.
Yeah, dimension one would be a good starting point, entry point to this type of questions.
Yeah. Yeah, and in some related models, there's a lot known in dimension one, whereas in dimensions 2 and higher, things kind of go crazy and just don't know how to deal with it. Right?
Yes, that's quite typical statistical mechanics.
Yeah.
Well, thank you very much again. And I want again to congratulate the winners and thank all the participants, and thank you sponsors and Sasha for this opportunity to have this competition and to have this meeting. And I hope to see all of you or many of you next year. Thank you. Bye-bye.
Thank you.
Thank you. Bye.
Bye-bye.